Irodov problem number 1.68. At the moment t equals 0, the force F equals AT is applied to a small body of mass m resting on a smooth horizontal plane. A is a constant. The permanent direction of this force forms an angle alpha with a horizontal as shown in the figure. Find the velocity of the body at the moment of its breaking off the plane and the distance traversed by the body up to this moment. Okay, we'll start with the diagram. So here's a mass m and a force, which is a variable force, is applied on this mass and it makes an angle alpha in this direction. Okay, we have to find out the moment when the mass breaks off the surface and velocity of the body when this body breaks off the surface, and second we have to find out from t equals 0 up to that point when it breaks off the surface what's the total distance traveled. Okay, so we'll do a free body diagram of the mass m. So mg, there is normal reaction, and then there is this variable force F, which always makes an angle alpha with the horizontal. Okay, and this force F is varying as AT. Okay, and also given at t equals 0, velocity was 0. Okay, all right. So if I write the equations of motion here, so n normal reaction plus F sine alpha, which is component of this force in this direction, minus mg. Okay, so that's the net force in the normal direction. Let's say the net force is 0, everything is balanced out. Okay, so which means what? The body is still on the surface. When will the body leave the surface? When n becomes 0. Okay, okay. So when will n become 0? When F sine alpha minus mg is 0, or this is equals to mg. Okay, so I know F I can substitute as AT sine alpha equals mg. So at time mg by A sine alpha, the body leaves the surface. Okay, okay. So let's call this t as t dashed. So at t equals t dashed, what is the velocity? We have to find out. Okay, now what is contributing to increase of velocity? What is contributing to increase of velocity is the component of F in this direction. So which is F cos alpha. Okay, now this is responsible for the acceleration of the body in this direction. Let's consider that acceleration as w. I'm not taking a because a is a constant here, so let's say it's w. So this is equals to mw. Okay, now w we can write that as m dv dt. So F cos alpha is m dv dt. Now we can write dv is equals to F by m cos alpha times dt. Now we can replace F as AT, so this becomes A by m cos alpha times t dt. Okay, Now let us integrate both sides. So velocity is from 0 to v dashed and time is from 0 to t dashed, and t dashed value we have here. So this becomes v dashed is equal to a by m cos alpha is a constant, and this becomes t square by 2. So we can write t dash square by 2 minus 0. So it's t dash square by 2. So which is equals to a by m cos alpha. Now, or let's say a by 2m cos alpha times t dash square. So t dash square is m square g square divided by a square sine square alpha. So m, a, we can cancel. We can write this as mg square by 2a, and cos alpha if I bring down, we can write this as 1 by sine alpha times tan alpha. Okay, so that's my value of v dashed. Okay, now the third part of the question is, so from here, if I just let's say do at any time, so velocity at any time is equals to ma by m cos alpha times t square by 2. Okay, now velocity we can write as ds dt a by 2m cos alpha times t square, ds which is the displacement or the distance traveled, we can write a by 2m cos alpha t square dt. Okay, now let's integrate both sides. So 0 to total distance s and 0 to t dashed. Okay, so the total distance covered is a cos alpha by 2m. This is t cube by 3, so into 3 and t cube, so t dashed cube. So this, if we simplify, we can write as a cos alpha by 6m. Now t dashed cube is m cube g cube by a cube sine cube alpha. So m square a square. So we can write, let me write the result here, s equals m square g cube cos alpha by 6a square sine cube alpha. So that's the total distance traveled from the beginning of motion to up until the mass leaves the surface. Okay, so that is our solution.